right, so the Oppenheimer movie is coming out, and there's a lot of YouTube videos about bombs and stuff, rekindled interest in the bomb. And I thought I would show a couple things that maybe you haven't seen before that I find very fascinating as an engineer. There's a lot of science to the bomb, there's a lot of politics to the bomb, there's a lot of things about the bomb, but the actual engineering, there was a lot of engineering that had to happen to make that bomb go, and untold amounts of engineering. And there's this really cool document. Now, this document has finally been unclassified, and what this is, here's all the unclassified markings. It was one thing in 1985, one in 1996. Anyway, this thing, if you go to Google and you put in the Los Alamos primer, type in Los Alamos primer, you'll get to a site on Wikipedia that will point you to this. They have links to this document. Now, what is this document? It's a 24-page document, and it is basically somebody's notes that somebody took when they took a lecture at Los Alamos. So imagine you have all of these scientists coming from all around the world, or not around the world, all around the country to work on the bomb, but they're not told what it is. They're just said, hey, your assistance is needed. We'll tell you what it's all about once you get there. And then they kind of had an introductory class, and it was this guy gave 5 lectures, and these are the notes this guy took of these 5 lectures. The lectures were given by Dr. Serber. And so, number one, the objective, why is everybody there? The objective is to propose a project to produce a practical military weapon in the form of a bomb in which the energy is released by a fast neutron chain reaction in one or more of materials known to show nuclear fission. So there you go. That's a great statement. You talk about writing a perfect statement, project statement. That's the perfect one there. It doesn't give when. It just says that's what they're working on. All right. And then it talks about why this is possible. Well, what about fission? Well, if you do the calculation, you find out the amount of energy, okay, that is number of ergs. Ergs is a unit of energy. Ergs per gram. So if you have a gram of material, like plutonium, uranium, things like that, you could get, contained in that 1 gram is 7 times 10 to the 17th ergs per gram. So if you could release all that energy, you would get 10 to the 17th ergs per gram. Now let's compare that with TNT. TNT is 10 to the 10th ergs per gram. And so it's 10 to the 7th more energy than TNT has. So it's obviously going to make a much better weapon. So 1 kilogram of 25. 25 was their code word for uranium-235. 1 kilogram of 25 equals 20,000 tons of TNT. So 20 kilotons of TNT. And then it talks about nuclear chain reactions and a bunch of things for fissionable cross-sections. It talks about high explosives. It talks about doing a gun-type bomb, doing an implosion-type bomb. How do you extract these isotopes of uranium and plutonium? All kinds of stuff in 24 pages. Everything you ever wanted to know about the bomb are in that 24 pages. It is outdated. It's been declassified. All the stuff might not have been totally correct when it was written, but I find it fascinating. These 24 pages, as a physicist, I find these 24 pages fascinating. All right. Today's video, though, what I wanted to talk about today is it seems as though everybody talks about Nagasaki, everybody talks about Hiroshima, and that after that, we did more stuff. We built an H-bomb, we built other things, we just did stuff. And no one ever talks about, well, what was that stuff? How did it proceed? What is the history of a tiny little bomb getting bigger and bigger and bigger and bigger? And then did they get bigger and bigger forever, or did they get smaller and smaller? There's the gun type and the implosion type. Was the gun type just completely abandoned? It was fired off once and then never again? What are all of these historical facts that people never talk about? So a friend of mine used to work on the bomb. He was in charge of renovating them. They had a shelf life. A bomb would only last a certain amount of time, and then it had to come in for maintenance, like an oil change. It had to come in, and you had to do some things to it. There was some replaceable parts and things, and that's what he did. He pointed me to this book. He says, here's the book you want. This is U.S. Nuclear Weapons, The Secret History by Chuck Hansen. He spent his lifetime going through all of and trying to get things declassified and reading all the declassified stuff and reading all of the stuff that was marginally declassified because it was leaked by the Pentagon or somebody else. And he put it all together in one book. And this is a great book. It's not cheap. It's hard to find. Well, it's harder to find, I would say. It's no longer in print. I think I paid $100 for this copy. It starts out talking about the physics of fission and fusion, of high explosives, and then it goes into the history. It's got tons and tons of pictures of all of the blasts, and cross sections of bombs. Like I said, all the Mark 8, Mark 10, up to Mark 80, 83. There are a whole bunch of more modern bombs. This goes up to about the year 1990, I would say. And he has a whole bunch of really, really cool information in here. Like here's a W-87, which is I think these are still in our arsenal, the W-87. Here's one that has multiple warheads with his reentry system. So you send up one rocket, but you have like 8 different warheads that target different things. Here's one for a submarine. Yeah, all kinds of stuff. So anyway, I wanted to give kind of a short little talk today about what happened. If you've watched the movie, I'm going to go see it in a couple days. If you've watched the movie, what has happened? What is all the info that's happened, okay? All right, here's some cool facts, okay? These are just kind of trivia. If you have Trivial Pursuit for the bomb, okay? How many atoms of fissioned atoms would it take to have 1 kiloton of TNT explosion? Well, it's Avogadro's number. It's 10 to the 23rd. So 10 to the 23rd atom splits gives you 1 kiloton of TNT. That's kind of a cool fact. The other fact is what's a shake, okay? Shake. A shake is the amount of time it takes for an atom to fission, okay? It's 10 nanoseconds. 10 nanoseconds, okay? So if you need that many atoms and you start out with just 2 and then 4 and then, it keeps building up geometrically, how many times do you get to 10 to the 23rd to get 10 kilotons, or 1 kiloton? If you want 10 kilotons, it's 10 times more than that. All right. Other facts. Little Boy. Little Boy was the one that had a block of uranium, and then it had a plug. And this plug went zooming in there, it caused critical mass and explodes, right? Everybody knows that one. Well, the plug was 42% of the weight of the whole thing, okay? So 60% down here, 42% up here, right? You think maybe the plug was a little bit nuts. It was 42% of the total mass, okay? And how much was the total mass? Well, the total mass was 60 kilograms, okay? A lot. 60 kilograms was a lot. And when this went in there and it did its thing and it exploded, it converted a whole bunch of this into energy. Well, there's a number called efficiency. How much of it did actually fizz and explode? What was the efficiency of the bomb? It was 1.2%. Really, really lousy. So if you were an engineer and your first result was 1.2%, you might be scratching your head. That didn't work out very good, did it? All right. The yield of the little boy was 15 kilotons. Okay, 15 kilotons. Okay, let's talk about Hiroshima. Hiroshima was the implosion bomb, all right? Well, you had 60 kilograms here of uranium, but the Fat Man was plutonium, and you only needed 6.2 kilograms, 1/10 of plutonium in order to do the same job, okay? And when they torched it off, they figured that they got 21% efficiency. Much, much better. So 1.2% here, 21% here. That's a really good result. I'm shocked by that number that it was so high. So plutonium just likes to go. So that was a good result. And they ended up with 23 kilotons, okay, for the Fat Man, okay? Little boy, Fat Man. Fat Man was the one we had concentric circle and all, implosion, that kind of thing, right? All right. Let's see here. Okay, but then what happened after that? What happened after Nagasaki? What did they work on? They had no more bombs. There was none in the stockpile. They'd used them all up. So what did they do? Well, they started making more bombs, of course, to get them in the stockpile and stuff. And they started, there was a hint that maybe an H bomb would be possible, a thermonuclear bomb would be possible, a fusion bomb. And that had been talked about for quite some time, but then they started to actually work on that in the 1950s. Yeah, let's work on a fusion bomb. And so they, believe it or not, they did not abandon the gun type design. They had a program where they wanted to have all different types of bombs. You can't just have one size fits all. They wanted some that were aerial bursts, some that were ground bursts. They wanted some in the water. They wanted some that you could fire from a cannon. They wanted all sorts of different bombs. One of the bombs they wanted was a pointy bomb, okay? They wanted a bomb that was really, really pointy, and it could go down inside the earth before it exploded, to go into big bunkers and stuff like that. Okay, and so they made these weapons. They were good for about 100 feet. They would penetrate about 100 feet down in the dirt, and then they would explode. Okay, and they were kind of these long, pointy tubes, right, like dart. And they thought that the gun type device, having a thing, you know, kind of like this, having that plug in there and having a narrow diameter and everything, the gun type design would be better for this. And so they continued in the 1950s building a bunch of gun type devices. And uranium, you needed too much uranium. The plutonium was just the way to go. So they worked a lot trying to build a plutonium gun device. And plutonium doesn't like this at all for various reasons. If you had perfect plutonium, what is plutonium number? I forget the numbers now. But if you had the pure isotope of plutonium, you could build one. But it's usually contaminated by a bunch of the bad plutonium, and the bad plutonium just doesn't like to do this, and the thing explodes before it fuses. So, they tried really, really hard. But after about, I think they worked on it for about five or so years, they finally abandoned this. All right, they figured out other ways to do it. What else did they work on? Well, they had to work on building the bomb smaller and smaller and smaller and smaller. And they figured out that the way to do that was really what you needed to do is just have bigger and bigger and bigger high explosives. You needed to have a good compression. If you have a sphere of plutonium and you need to squeeze it down, how much squeezing do you do? Is it 30%? You know, squeeze it by 30%? Is it 50%? How much squeezing do they do? Well, this is really shocking. Between 8x and 27x. It gets squeezed down to 1/8 or 1/27 of its original volume. That is nuts. That is just nuts. Anyway, so they worked on that. Then they started working on the H bomb, okay? The hydrogen bomb, fusion. And they just determined that you need to fuse hydrogen into helium. That's what you need to do. And starting with just raw hydrogen won't get you there. You need to have an isotope of hydrogen. You need to either have deuterium or tritium, and maybe a combination of both. And so they thought, okay, yeah, let's work on that. And then they figured out that if you had 1 pound, okay, 1 pound of deuterium and you could fuse that. Let me look at my notes here. 1 pound of deuterium is 68 kilotons. So, 6 times the size of the Hiroshima bomb with 1 pound of deuterium, right? So they were doing those calculations in their head and stuff. And they wanted to figure this deuterium thing out, okay? Let me find some other paper. I can write at the back of this. Am I right back? No, this is all printed back. Okay. So some people said, well, if we can get deuterium to light, and we have a rod of deuterium here, okay? If we can get one end of the deuterium lit, then it will go whoosh and burn like a fuse, and it'll fuse along the way. You'll get all kinds of stuff, and you can make this super long if you want to. It would just keep burning, right? And so that's the idea they had, but they needed a really good way to light this thing off, right? And so they said, okay, great. We'll just put a bomb over here. We'll put an atomic bomb over here, and that will light the deuterium, and then the deuterium will run like a fuse, and it'll go whoosh, whoosh, and you'll get a big explosion, right? 1 pound is 68 kilotons, so 1 pound, 2 pound, 3 pound. Yeah, you could just put as much as you want in there, right? All right, so they worked on that. Didn't work. Did not work. And then they worked on making the bomb smaller and smaller and smaller, okay? And one of the tricks that they learned was if you're going to build a bomb, so here's your plutonium, and you're trying to squeeze it with all of this high pressure here, okay? You squeeze it down, and it doesn't do anything. It needs like a trigger. It needs like somebody to tell it, hey, why don't you get those neutron things going? And once the neutrons start whacking into one another, then it takes off. But you need to like kickstart it, okay? And so they figured out if you put a little bit of goo in the middle, okay, that makes it make some initial neutrons. So while it's collapsing, it's building up some neutrons. Now, once it gets going, it'll make its own neutrons, but you need to kickstart it. So there's this thing here called the initiator, or the pit, or the urchin. A bunch of words for this little thing in here. It's got some plutonium in it. It's got some beryllium in it. It's got some other things in it. And that was the way that they were getting the thing to go, okay? That's this little thing here, get it to go. And they needed to decrease the surface area of that and everything. A bunch of science went into that. And then they said, wait a minute, we have a better idea. We got a better idea, okay? So we're going to start with some plutonium, and then over here, okay, we're going to have a light bulb, and this is going to be a special light bulb. It's going to spray out neutrons. So it's going to be like an electron gun, except it's a neutron gun, okay? And they made these things, they're these tubes, and you put high voltage on them, and it creates, I think, some high-speed electrons that bash into some thing, and the thing they bash into, beryllium or something, releases a whole bunch of neutrons, and the neutrons then spray. Now, the neutrons can go right through this plutonium, and so while this thing is compressing, you then spray in a bunch of neutrons from the outside world, and that gets it going. And so most bombs are built this way. They have this neutron initiator, neutron tube initiator on the outside. I'll show you one of those later. And then they said, okay, well, what else can we do? Well, we can have rings of stuff. They figured out having different layers of different things, some plutonium, some uranium, some even aluminum and stuff. But the cool thing they figured out is let's leave the center hollow, because then you could start with something that wasn't critical, and then it would collapse on itself really, really fast because there's just a hollowness in there. That last little clunk would just kind of like a submarine. You just go crunch, and then it would become really, really dense really, really quick. And they thought, that worked really, really good. And then somebody had an idea. Well, since we have a hole of a vacuum inside this thing, let's drill a hole in it, okay? So they drilled a hole in it, and they said, okay, what we're going to do is we're going to hook this up to a compressed tank, okay? And in this tank, we're going to put deuterium and tritium, and in gaseous form. And when the bomb starts to go off, when it's starting to collapse, And just before we spray it with neutrons, we're going to inject deuterium and tritium into the center of the bomb, and it's going to get compressed, and then we're going to spray neutrons on it, and then the whole thing is going to go up, and it's all still collapsing and everything, and it will fuse. Okay? And so this fission bomb now has a little bit of fusion inside of it. And this is called a boosted bomb. A boosted bomb, okay? And so these are very, very common. Almost everything is built this way now, where you have a hollow center, you have some goo that you can spray in there, and then the neutron thing. And then this whole thing can have a dial on it from like a little bit to a lot. So you can inject more of this, you can inject more of this. And so most of the bombs are dial yield. You can actually set the yield of the bomb, say between 10 kilotons and 1 megaton. You just dial it to whatever you want, and it can do its things, okay? All right, so a boosted bomb can get you up into about the 100 kiloton range, just all by itself, just a pure fission bomb with a little bit of fusion, okay? A little bit of fusion can get you up to about 100 kilotons, okay? To get up to the megaton range, then you need to have a true hydrogen bomb, okay? Okay, how do you build a true hydrogen bomb? Well, they tried the super and they tried the alarm clock and they didn't work. And in 1951, they came up with an idea of how they could actually make this thing work. So, up till then, they knew of two ways to make a fission bomb. You could either make a gun-type device with a plug, or you could make an implosion device. Those were the two ways they knew how to make a fission bomb, how to get plutonium or uranium to fission. But it dawned on them, 1951, that you could get them to fission a different way. If you could just get it hot enough, if you could just put in enough energy, you can actually get those materials to fission, okay? So, if you had a atomic bomb here, okay, and you had some material that you wanted to fuse, you could put it in the middle of the bomb, and then as it's making a fission bomb, it's also fusing. And that's a lot like the fusion bomb that we just heard, the boosted bomb. The boosted bomb uses that. But people tried to put more stuff in there to get a fission fusion bomb. But you're lowering the density of the fission and it just doesn't work. So the big invention was, well, if we have this over here and we put our deuterium over here and then we put it in a chamber, then this thing will output a whole bunch of X-rays, okay? And those X-rays will get focused over here in this ellipse. And all of those X-rays can cause, we're going to surround this deuterium, we're going to surround this with U-238. U-238 doesn't like to fizz very much, right? But by imparting all of these X-rays, you can actually get 238 to turn into a bomb. So it was a way to use this real crappy uranium as a bomb, and then you could just stack it with deuterium and tritium and stuff, right? And they said, hey, that's a good idea. We could do that. And then they had even a better idea. Okay, so here is the final configuration. This is called the Teller-Ulam configuration. Okay, the Teller-Ulam configuration is you have a fission bomb here, and then over here you build up something that looks like this. Okay. So this is a cylinder. This is a cylinder, okay? And in the center is plutonium, and in a concentric circle around is uranium, and in here is deuterium and tritium, and it's going to be in there a special way. We'll talk about that a little bit later. But basically, you have this fission bomb, okay, so this is the A bomb, and it outputs all of these X-rays, you're going to put this thing in a chamber, so all these X-rays get focused over here. Now, what do? Well, they smack into the uranium and cause it to start to explode, starts to fission. This thing's actually hollow. Some of them can actually come in the middle down here. But anyway, they go everywhere. So they hit the plutonium and they start it to explode. So you have the plutonium rod in the center. This is called the spark plug. The spark plug starts to explode and the uranium starts to explode. And so basically you have a center thing in the middle, and then you have a pipe on the outside, okay? And this starts to explode and that starts to explode. Well, this sends a shock wave this direction and this sends a shock wave this direction. And so the whole thing is imploding on itself. So this is going out, this is going in, and so the stuff in the middle gets compacted just to a thin little tiny little layer. It just gets super, super compacted, okay? And when it gets compacted enough, it starts to fuse. And when it starts to fuse, it outputs X-rays. Those X-rays then cause these guys to fission more, which causes more fusion, which causes more fission, which causes more fusion, which causes more fission, and the whole thing just goes boom! And there's about 9 of these explosion things boop, 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 before the bomb actually destroys itself. So you get a whole bunch of this. It's a fission, fusion. Anyway, there's multiple generations of these events, and the thing finally goes off. Now, they wanted to try this out, okay? So in 1951, 52, I think it was 1952, they said, yeah, let's give this thing a try. And they had a trick up their sleeve. Instead of putting deuterium inside this thing, they put in lithium. They put in lithium-6, lithium-7. Lithium, if lithium splits apart, it creates some deuterium and it creates some tritium. So you could have a solid form of lithium, and when it's inside this thing and gets compressed and heated up, it will release the right things. It will release tritium and deuterium, which is actually what you want. And so it's a solid state version of the boosted gas version, okay? And so that's what it does. So really, really clever, made everything super, super simple, okay? But the very, very first one they set off, they didn't want to use lithium because they weren't quite sure of the math. They wanted to have a pure science experiment. They wanted to have pure deuterium in this configuration. They wanted pure deuterium. So they spent $1 bazillion. They went to an island somewhere in the Pacific. Then they built a big thermos bottle, okay? They built this big thermos bottle, okay? And inside the thermos bottle, they put in liquid helium. They got liquid helium in here, which is super, super cold. And then they had a plutonium rod down the middle. They encased the whole thing with uranium. So they had the uranium, plutonium, uranium cylinder thing, right? And then in here, okay, in a bomb today, there would be lithium in there, but they wanted to do a pure science experiment. So they said, we just want deuterium in here, just deuterium. And it has to be cold. So they piped in deuterium liquid at minus 423 degrees Celsius. Okay? That's pretty cold. And then they torched it off. And they got 10 megatons. 10 megatons. Remember, they were doing kilotons before. They got 10 megatons out of this thing. So it obviously worked really, really good. And then they could get a whole bunch of science out of having this pure. And they destroyed the entire island. The island disappeared after they torched off this thing. But anyway, that was the experiment they did. That was in the Ivy test. This is the Mike bomb. It was about 20 feet high and 6 feet wide. That was just the thermos bottle. And then they put all this other stuff around it. So yeah, it was pretty big. Pretty big. All right. So did they stop there? No, of course not. Well, they made them smaller and smaller and smaller. And made more and more and more of them. But basically, today you can think of the bomb as something that has a bunch of spheres and something that has a whole bunch of cylinders, okay? So spheres over here makes a fission bomb. fizz, and over here goes the fuse. So fission fusion, and that's the way the bomb is built. You can actually put more here. Russia made one that was super, super big. 58 megatons was the Tsar Bomba. They had a, so this is sometimes called the primary and the secondary and the tertiary. So if you can put in more as well if you want, but a tertiary bomb is really, really big. The shapes of things have changed. You can have round and cylinder. You can have round and round. You can just have round. You can just have cylinder. And the cool thing these days, or one of the cool things, is remember, if you've watched the movie, you will see this, where they have a little pit of plutonium and then they have a whole bunch of high explosive wedges that you put in there. And I think they had 32 detonators, and these 32 lenses collapsed down, okay? Well, they can build bombs now with two detonators. One detonator on this side and one detonator on that side, and they can use an egg-shaped pit, because the whole thing's going to deform. It's going to be blasting from this way and blasting from this way, and so they make it kind of an oblong pit, and then after it finally gets smushed in, it'll be a sphere, and then it goes boom. And so, yeah, you can have a two thing here, which is nice because that fits into narrower tubes like rockets and howitzer shells and things like that. So, yeah. Let's take a look at a drawing that somebody made. I forget where this one was leaked. It was at some conference once, and somebody leaked it. And they said, here. And then people say, yeah, this is pretty typical of what's going on. So here we have a atomic bomb, the fission bomb. It is elliptical. It's probably a 2-point implosion. You have an egg-shaped center. You have reflectors and tampers and things like that. But this is the primary. You have polonium in there. You have a gas tank down here full of gas, and it injects it into a hole into the center chamber. That's the tritium and deuterium gas. That makes it into a fusion, a boosted fusion. You'll have a they don't show it in here, but you'll have a way of have a neutron starter on it. And once that gets going, and that is in this kind of elliptical package, and that focuses all the X-rays down over here, and then you have the spark plug in the center, and the pushers and tampers and stuff, and U-238 on the outside, and lithium on the inside, lithium-6 deuteride. Anyway, so fission and fusion. Modern bombs can be anywhere about 5% of its yield is this, and 95% of its yield is this. But smaller bombs, more tactical bombs, it can be more like 50-50. It just depends on what kind of bomb you're building, of how much is due to fission and how much is due to fusion. All right. And then let's end this is a long video. Let's end it with a couple pictures here. Here's North Korea showing off their bomb. I want to have you pay attention to this black thing here with a wire coming out of it. That's the neutron source. That's the thing that beams in the neutrons. It's on the outside. It beams it in. And here is the primary with a neutron source back here. This is the primary. The secondary would be over here. It's unknown. We believe that they didn't actually get the secondary working. They just did a boosted primary. But they're certainly working on a two-stage system. You always have pictures of guys standing around bombs. So here's another one of guys standing around bombs. These guys are standing around this little bitty tiny one. He's 6 inches in diameter and only 2 feet long or something like that. He was a tiny, tiny little bomb. That's one of the smallest declassified bombs I could find. Forget what the project name for this was, but it was to be fired with a recoilless rifle. And it's actually sub-kiloton. Its output is no more than 1 kiloton. But it's still pretty good bang for its size. And then if you're really brave, you would put it in a sack, strap it between your legs, and jump out of an airplane with it. So this guy is going to go into some site, carrying a bomb. He's going to then stick it somewhere and set its timer and then run like hell, and then the bomb will go off. So yeah, that was actually a thing they did back then, or at least talked about, was having some type of backpack bomb. So you might hear about that. I think the actual bomb part itself was about 50 pounds. And then there's casing and stuff around it. But I think 150 pounds for a backpack one, I think was typical back in the when was this? I don't remember what date this was. Probably around 1990, 1980. Maybe in the early 1980s they did this one. Yeah, there you go. More about the bomb than you ever wanted to know. But I think it's interesting that nobody ever talks about the continuing history of bombs, not just the oldie moldy one. There's a lot more interesting things going on today.